All right, so we're recording right now. So if you remember from last, what was that, Thursday? We went over the residual, and the residual is just telling you how much error do we have. So it is telling us how much error do our data set have. Pretty sure I spelled that wrong. You want to follow direction on the test. Like in the test, I put particularly like how I want the question answered. So just look at the question and it'll tell you how I want it to be formatted. Right. So whenever we calculate the residual is telling you how much error do we have. So whenever we calculate a residual, you're kind of looking for a residual that's close to zero, because the closer to zero, the better, because it's telling you there is no error. Like the further away you get from zero, that's kind of telling you that there is error and there's a significant amount of error. So when we calculate the residual plot, you're kind of looking for that. So you want the plot to show that all the data set is near zero, because if all the data set is near zero, that means that all of the data were pretty close to it. If we do have any data set that is not close to zero, that's kind of telling you that is doing a bad job at making prediction. So the residual plot should help us in regard to that. So the residual plot should show us how much of an error do we have. So whenever we do the residual plot, this is how we're going to do the residual plot. In the x-axis, you're going to put your x value. And if you remember, that's called the explanatory. Okay, so that's called the explanatory variable. So on the x-axis, that'll be the explanatory variable. For the y-axis, that's where you're going to put the residual. Let's see. All right, so that's taken care of. All right, so that's how we're going to do a residual plot. So the y-axis is going to correspond to whatever the residual is. The x-axis is going to correspond to whatever the x value is, which is our explanatory variable. So whenever we do a residual plot, we want all the points to be pretty close to pretty much the line. Because the closer all the points are to the line, that's kind of telling us that the predictive model or the linear model is doing a good job of making a prediction. Once our point kind of get further away from that, so if we get a point that kind of looks something like this, that's kind of telling us it's doing a bad job, because it's kind of telling us not doing a good job making prediction. So that's what we're looking for when we're doing a residual plot. All right, any questions so far for the residual plot, or like the basic of a residual plot? All right, so let's go ahead and do a residual plot. All right, so if you look at this example, it said the table showed the reaction time of a person before and after eating a meal. So we kind of want to see if their reaction time is affected by them eating a meal and by them not eating a meal. So we want to see what type of reaction time, does it get worse or does it get better? So if you look at the X value, the X value, we put reaction score prior to eating the meal. If you look at the Y value, we put reaction score after eating the meal. Okay. So if I wanted to find the linear model or the least square regression line, how can I find the least square regression line using our calculator? If you want, you can either shout out the answer or you can just put it into the chat. So how can I find the least square regression line? Thank you. But yeah, so we could do ln reg ax plus b. So what you want to do, you want to enter this into L1. You want to enter this into L2. Once you enter that to L1 and L2, you go to ln reg ax plus b, and that will give you our least square regression line. Fortunately for us, I already gave you that. So I already told you the least square regression line, just to kind of speed up the process. So what we want to do, if we want to find the residual, if you remember for the residual, you have to get the predicted value. Once you get the predicted value, you do y, which is the actual value minus the predicted value. So let's go ahead and let's find the predicted value for this one. So we'll say 0.3. And what should I let x equal into for this one? If I'm doing the first row. Perfect, yeah. So you want to let x equal to 3. All right, so if you do 0.3 times 3, you get 0.9. 0.9 plus 3.4. Oops. You get 4.3. All right, so that's my predicted value for that first row. So if somebody score a 3 before eating a meal, we're predicting that the score should be a 4.3. Any question where the red 4.3 come from? All right, let's do the second row. So for the second row, we're going to say y hat is equal to 0.3. In this case, what should I let my x equal now? Perfect, 4. So we do 0.3 times 4 plus 3.4. If I do that, well, that algebra, what would I get? Cool, 4.6, perfecto. All right, so let's go ahead and do the next one. So the next one will say y hat is equal to 0.3 times 2 plus 3.4. If I do the math for that one, you get 4. Perfect. All right. So then the next one will say y hat is equal to 0.3 times 1 plus 3.4. Want to check the math on that one, Julian, again? What do we get? There you go, 3.7. Oops. Hate that. All right, 3.7. All right, so the next one is 5. They say y hat is equal to 0.3 times 5 plus 3.4. And you're going to get 4.9 for that one. Good job. Yeah, they keep it with green. Then we say y hat is equal to 0.3 times 7 plus 3.4. You get 5.5. All right, so you got y hat is equal to, let's say, 0.38 times 9 plus 3.4. You get 6.1. You get 6. Yeah, y hat is equal to 5.2. And lastly, the y hat is equal to 5.8. Any questions so far how I found the predicted value? All right, no questions. Perfect. All right, up next, what we're gonna go ahead and do, we're gonna go ahead and calculate the residual. So the residual should be pretty simple because I'm gonna get this value over here and I'm gonna subtract it by this value over here. So if you look at the first one, we're gonna say 5 minus 4.3, that's positive 0.7. Almost wrote a negative. All right, so then the next one will be 6 minus 4.6, and you get 1.4. Next one you want to do is 3 minus 4, and you get negative 1. Then you want to do 4 minus 3.7, and you get 0.3. Then we could go ahead and do 4 minus 4.9, and you get negative 0.9. Then we could do 8 minus 5.5, and that's 2.5. Then we could do 5 minus 6.1, and this is equal to negative 1.1. And then we could do 2. So we do 2 minus 5.2, and get negative 3.6. Oops, that is wrong. Should be 3.2. And lastly, we could do 7 minus 5.8. 7 minus 5.8 is 1.2. So far, any question on pretty much how I got any of the number in paint? Oh, paint. All right, so up next, we're gonna go ahead and do, well, let's kind of just recap what we just found. So the column that I just found, that's your residual. So that's just telling you how far off our predicted value was from the actual value. So you kind of always want them to be close to zero because the closer it is to zero, the better. Like the further away from zero it is, like the worse, because you want them to be positive. Well, sorry, you want them to be close to zero. So let's go ahead and we're going to use this chart over here to draw this out for us. Please remember, this is the X value. And this is our residual. All right. So let's go ahead and do the first one. So the first one, I'm going to highlight the row so that way you know exactly what I'm talking about. So if you look at the first one, my X value is 3. My Y value will be 0.7. So my first will be 3 and 0.7. And that's right there. So that's my first plot for my residual plot. Any question in regard to that first plot? All right, so let's go ahead and do the second plot. So if you look at that second one, is actually going to be X is 4, my Y is 1.4. So 4 and 1.4 is somewhere right there. So that's my second plot. Let's go ahead and do the third plot. So the third plot was 2 and negative 1. So 2 and negative 1. So here go 2, negative 1 should be right below. That's 2 and negative 1. All right, up next, we're going to go ahead and do the next row. I'm going to do 1 and 0.3. So 1 and 0.3 somewhere right here. Then we have 5 and negative 0.9. 5 and negative 0.9. Negative 0.9. Then what we have 7 and 2.5. So 7, 2.5 is there. Then we have 9 and negative 1.1. So 9 and negative 1.1. Then we have 6 and negative 3.2. So 6 and negative 3.2 actually go down. And lastly, we have 8 and 1.2. So we have 8 and 1.2. Here, let me make the dots a little bit thicker or bolder. All right, and that's how you do a residual plot. So residual plot is a good way to kind of see how accurate our least square regression line was. The more accurate it is, the closer it should be at 0. The least accurate it is, pretty much the further away from 0 it should be. So by looking at this residual, well, any question on how I constructed the residual plot? And in a little bit, I'll show you how to do a residual plot in your calculator. It's actually pretty fast and easy, as long as you just know the steps. But yeah, all right. So what the residual plot kind of telling me, it should tell me like whether the least square regression line is doing a good job or if it's doing a bad job. So kind of telling us if the least square regression, is this the model that we want to use, or should we look at another model? So by looking at this residual plot, you should kind of see that since all of the points are kind of close to 0 or pretty close to 0, like the only two that are kind of a little bit suspicious, and let me get yellow again, are these two. But if you look at mostly everything else is pretty close to 0. So in this case scenario, we will say that a least square regression line is a good model for this data set. And that will be if in regard to what do we use the residual plot for. So let me actually write that down so that way if you're wondering what to write, I'll take that suspense away from you. So we'll say based on the residual plot, it looks like the least square regression line is a good model for the data. And also, just remember, this is kind of going back to that we only have a sample. So based off of this sample, we're trying to make a conclusion about the population. So we're trying to say, okay, based off of this sample, we're trying to say, would the population resemble a linear pattern? And based off of this, we're kind of going to lean toward yes, the population most likely have a linear model or a least square regression line. All right, but that's it for that linear model of the residual plot. Any question in regard to the residual plot? All right. So let me see what's next. Wait. All right, so what we're gonna go ahead and do, we're gonna go back to that problem, and what we're gonna do a residual plot using our TI-83 or TI-84, whichever model you have on your calculator. All right, so if you look at the instruction, it says first press, first thing first, you have to enter the data set to L1 and L2. So in a little bit, we're going to go back to this original data set and we're going to enter X into L1 and Y into L2. Once you enter the data set, what you want to do, you want to go second you want to hit the second button, you want to hit stats, and you want to hit resid or residual. So that will calculate the residual for you. But before you do that, you first have to hit ln reg ax plus b. So I'll show you how to do that with your calculator in a bit. So let me go ahead and transition over to the calculator. All right, so everybody should see my calculator. So I'm gonna go to stats. I'm gonna go to edit. I wanna delete this data set, so I'm gonna press up, clear, enter. I can do that again, up, clear, and enter. So let me go ahead and enter the data set. So the first one is 3, 4, 2, 1, 5, 7, 9, 6, and 8. So that's my data set for L1. Now I'm going to enter my data set for L2. L2 will be 5, 6, 3, 4, 4, 8, 5, 2, 7. All right, so first thing first, enter the data set into L1, L2. Any question how to enter the data set into L1 and L2? All right. So first thing you want to go ahead and do, you want to do the ln reg ax plus b, because you want to calculate the predictive value, because if you don't do this, when you're trying to do the residual, it's not going to work. So I'm going to go to stats, going to go to calculate, and we'll do number 4, ln reg ax plus b. If you don't do that, it's not going to give you the residual. So X list is L1, Y list is L2. All of that look correct. We'll go ahead and calculate. So if you look at A is 0.3, B is 3. Well, essentially 3.4. R is 0.43. Everybody good with that so far? Okay, so now we're going to calculate.
Wait, I actually got the opposite for some reason. I got A 3.38 and B I got 0.3. Does that make any difference?
No, because I'm pretty sure for yours, if you look on top, it should say Y is equal to BX plus A, correct?
Oh, this one says, yeah, A plus BX. Yeah.
Yeah, so like for my A, it go next to X.
Uh-huh.
For your A is by itself. So that's why saying A is 3.388.
Oh, okay.
And
Okay.
you're saying A is the y-intercept. So the y-intercept is 3.388. A is that you chose the different one.
Okay. All right. Thank you.
Yep, no problem. All right, so now we're gonna calculate the residual. So I'm gonna go ahead and calculate the residual. So I'm gonna press second, and I'm gonna press stats. So if you look all the way down here in the bottom, it's a resid. So that's the residual. So I'm gonna go over here. I'm gonna select the residual. So if I want to, I can just press enter, and it will give me all of the residual value. And then I can just scroll by, and you have all the residual value. But the thing is, I want to use this for my L3 because I want to create a scatter plot of this data set. So what I'm going to do that again. So I'm going to go second, stats. I'm going to do reset. Oops. But now what I want to do, I want to store this into one of my lists. So the list that I have available is L3. So I'm going to tell my calculator to get the residual and put it into L3. So that way I could graph it. So what I want to do, if you look right above the on button, it should say STO. STO is for store because we're storing the data. So we're going to say STO. And then what I want to do, I want to enter it into L3. For me to select L3, I have to hit the blue button or the second button and then hit 3. And now what I'm telling my calculator, I'm telling get the residual and I want you to enter it into L3. Any question in regard to that? All right, so I'm gonna press enter. And now all of this data set should be in L3. So I'm gonna double check that. So I'm gonna go stats. I'm gonna go to edit. And if you look at L3, all of these are my residual. So if I wanted the residual for 3, the residual when x is equal to 3 is 0.711. If I want the residual for 7, which is this one, I go over here and the residual is 2.51. If you actually look at what we got, this should be pretty much close to what we got with our when we did it by hand. All right, but everybody good on how to get L3 with the residual? All right, so up next, what we're gonna go ahead and do, we're gonna go ahead and make a residual plot, and we're gonna use a calculator to do the residual plot for us. So I want you to hit the second button, which is the blue button, and I want you to hit Y equal. And if you look right now, I have plot on for the first one, so I'm gonna just use that one. So plot is on, but I wanna go down, and I wanna use the scatter plot. So the scatter plot is actually the very first one that we have here. So I'm gonna select the scatter plot. So if you remember for the residual, if I wanna graph the residual, my x-axis is gonna have the x value. My y-axis is gonna have the residual. So for the x list, you leave it at L1. But for your y list, I had to change it from L2. And which one should I tell it to look at? Good, there you go, L3. So let me tell it to look at L3. All right, cool. And that's pretty much it. If you want, you could change it. If you want to put a plus sign, you could use a plus sign, but it really doesn't matter. All right, everybody follow so far? Okay, so last thing, go to graph. So if you look at graph, there's nothing there. It's because the calculator is not focused on the right area. To make the calculator focus on the right area, you have to hit the zoom button, and then all the way down where it says zoom stats, you have to select that. And now there's our residual plot. So if you look at that residual plot, and if you look at the residual plot I did, they pretty much look the same. Like we kind of pointed out that these two data sets that are kind of further away are kind of making this not linear. But since most of the other data sets are pretty close to it, we're going to say it follow a linear path. All right, but that's it for that. How to do a residual plot on your calculator. Any question on the residual plot on your calculator? All right, so you go second, y equal to, you go plot on. If you want to change the y list to L3, what you have to do, you have to hit the second button and then hit the number 3, and that will change it to L3. If I want to change it to L4, you hit second and you hit 4. Let me change that back to L3. So yeah, so all you have to do where it says the Y list, you want to select L3. So to select L3, you have to hit second and you hit number 3. And that's it for that one. Any other questions? All right, sweet. All right, so now usually for a test, what I'll do, I'll usually give you the residual plot. So I'll give you the image of a residual plot, and based off of the residual plot, you should tell me if it does follow a linear path or does it not follow a linear pattern. Yeah, good question. All right, so let's get into that. All right, so let's do share. All right, so if you look at the graph I did by hand, if you look at the graph that we did on the calculator, they should look kind of identical to each other. Like it's not gonna be 100% because pretty much the residual plot that we did with the TI-84 is a lot more accurate because there's no human error in that one versus the one that we did by hand. There's human error because I rounded it off when I'm putting the plots and not exactly at like 0.7 or 0.4. So just know there is going to be some human error when you draw it out by hand. All right, so let's go ahead and look at some residual plot. All right, so in a test or in a quiz, when you're looking at the residual plot, you're going to look for something called constant error variance. When you see the word constant, what does the word constant, like, what does that resonate with you? Like, what's your meaning of constant? Well, if they tell you somebody is constant, what does that kind of mean about that person? Cool. So they're just saying, so repeat is pretty much is always happening. It's consistent. There we go. So when we say constant error variance, what we want to see that there's just pretty much there's a similar or a consistent distance for the residual plot. So we don't want to see them all scatter all over the place. You kind of want to see them where they're all consistently near the line. So if all of our data set are consistently near the line, we're going to say it has a constant error variance. If we see data set or if we see a residual plot where the point these seem to jump all over the place and you could kind of see a pattern, we're going to actually call that where we say that the constant error variance is violated. All right, so let's go ahead and look at it. All right, so here we go, a regular X and Y scatter plot. If I look at this scatter plot, does it look like a linear line or does it not look like a linear line? All right, so we got no. So we'll say does not look like a linear, oops. Yeah, if you look at it, it's more like a curve. Technically, the name of this graph or the name of this model, it will be called parabola. So it looks nothing like a linear line. So if you look at the residual plot, that's the residual plot that I got. Does it look like the variance is constant? Does it look like all of the points are near the line? Or are they pretty much just all over the place? So what do they look like? Yeah, so they're up and down. So pretty much they're all over the place. So in this case, we have a constant error variance, and this is violated. Because if you look at it, the variance is not constant. It is pretty much changing. Because if you look right here, this one has more variance than this one, than this one. So the distance for each one of these residual from zero, they're not the same or they're not similar. So that way for this one, we say constant error variance is violated. So now we're gonna go ahead and see one that the constant error variance is not violated. All right, so let's look at this. So if I look at that scatter plot, and we're gonna call it scatter plot A, does that look like a linear line? So we'll put this scatter plot, Yeah. Cool. All right. So almost everybody agreed that this scatter plot looked like a linear line. So let's go to the residual plot. So this is the residual plot. Let me just label it just for that way you know for sure the residual plot. So if you look at the residual plot, are all the points pretty close to zero? Or are they kind of like all over the place like they were in the last one? Yeah, so if you look at it, most of them are close to zero. Like you do have this one over here, which is this point over here. They're kind of a little bit screwing it up. But if you look at it for the most case, all of these points are pretty close to zero. Since all of these points are pretty close to zero, for this one we'll say constant error variance is not violated. Because it's pretty much showing, the residual plot is showing that all of the variance is the same. Because pretty much the distance from the residual line, which is zero, to each and every point are pretty much the same for all of the points. So for this one, we'll say residual plot, the constant error variance is not violated. All right. Everybody go for that second example. All right, let's do this third example. All right, so what about this scatter plot? Does this scatter plot look like a linear line? Yeah, so we'll say this scatter plot so yeah, so we'll say this scatter plot does look like a linear line. But if I go over to the residual plot, does the residual plot also kind of show that all the points are kind of relatively the same distance away? Or is it kind of like all over the place like it was in the first one? So if you look at it, like pretty much all of these points are pretty close in distance. Because if you kind of look at this point, they're the same distance away from zero. So yes, it's not as close as zero as this last one was. But the reason why it's not as close as zero as the last one was is because we're actually using bigger number. Because once you start using bigger number, like the accuracy is not going to be as much as accuracy will be for a smaller data set. So you kind of have to just know that in the beginning. Like once you increase the number, it's actually going to be okay if we're off by a little bit more versus if you have smaller number, you would expect it to be closer to zero yet because you're dealing with smaller number. So for this one, if you kind of look at it, like all of them look kind of constant. You don't have like one that extremely far away and then other that are pretty close. All of them are kind of consistent in the range. So for this one, we'll say it's a linear model. All right. All right. So for this one, the length of a sand shark. So looking at this graph over here, so looking at that scatter plot, does that look like a linear line? Yeah, so we should say this does look like a linear line. So we'll say based on the scatter plot, So now let's go to the residual plot. If you look at the residual plot, are all of the points pretty much relatively close to the same distance? Or do we have like a big deviation like it was for the first one? Well, if you look at the residual plot, all of the points are pretty close to each other. Basically, if you look at this one, since we're dealing with kind of smaller number than the 300 and the 400, for this one, all of them are pretty close because if you look at it, like the residual is going from -2 to +2. So that's kind of telling me we have a close linear relation. So we'll say, all right, so we'll say the residual plot is showing a linear relationship. So for this one, if all of the points are kind of hovering around the same line, you say pretty much there is no well, that the constant error variance is not violated. But if you see data point where like the distance for all of the points are not consistent, like if you have some points that are like all the way up here and then you have some point all the way down here, in that case you want to say that the constant error variance is violated. All right. Everybody good in regard to that? All right. So the last thing we're going to do for this, we're going to do something called sum of square residual. So the sum of square residual is pretty much just telling us how much error do we have in this model. So for this one, if our model is a perfect model, what should the sum of square residual or SSR, what should that equal to if this is a perfect model? Because if this is a perfect model, should we have an error? Like, no, you shouldn't have an error. So if you have no error, that means the sum of square residual should just equal to 0. So if SSR is equal to 0, we have a perfect model. So you just kind of know the idea of it. Like I'll show you how to calculate, but same thing with like the residual plot. I'm not gonna expect you to do this on a test or in a quiz. But if I give you a question asking you about SSR, like I do expect you to know that the sum of square residual is represent like how much error is in your model. So the smaller the sum of square residual is, that's telling me the better the linear model is. The higher sum of square residual is, pretty much that's telling us the worse this model is for this data set. So you just kind of know the basic of what the sum of square residual is. Yes, no, the closer to 0, the better of a model is telling us that this model is. The further away from 0 it gets, that's kind of telling you the worse of a model is. So the way that we get the sum of square residual, well, if you kind of look at the word square, when you see the word square, what does square tell you? Like what mathematical operation should we do? So when you're close, you don't want to times it by 2, but pretty much what you want to do, you want to square it. So you want to take it to the second power. Perfect. So if you look at it, it says square residual. So that means we get the residual and you square it. And what does the word sum mean? Yeah. So in order to be able to calculate the sum of square residual, all you have to do, you have to get the residual. You have to take it to the second power. The reason why you're taking to the second power is because you want to get rid of all of the negative residual. And then once you get rid of all of the negative residual, what you want to do, you want to add them all up. And that will give us our SSR. So just remember, the closer it to zero, the better. The further away it gets to zero, pretty much the worse of a model it is that you have. So up next, we're going to go ahead and we're going to use the same problem that we used in order to calculate the residual plot. And now what we're going to do, we're going to calculate the residual, the sum of square residual. So if you look right here, I already calculated the residual. It pretty much should be exactly the same thing that we got when we calculate over here. So if you look at your notes, like these values should be identical to the value we got in the last run. So in order to calculate residual square, I'm going to get the residual and I'm going to square it. So I'm going to get 0.7 to the second power. That's going to be 0.49. Then you're going to get 1.4 to the second power. So 1.4 to the second power. You get 1.96. You get negative 1 to the second power. Well, that's 1. If you do 0.3 to the second power, that's going to be 0.09, if I remember correctly. Yeah. If you get negative 0.9 squared, that could give you 0.81. 2.5 squared. 2.5 squared is 6.25. If I do negative 1.1 squared, you get 1.21. 3.2 squared, you get 10.24. And then 1.2 squared, that should be 1.44. There you go. All right. Any question on how I got residual square? Or if you want the actual formula, it's over here. All right, so what I'm gonna go ahead and do, I'm gonna go ahead and just add these values to 0.49 plus 1.96 plus 1. Very cool. So somebody already calculated that for me. I'll go with their answer. We'll do black. So we got 23.49. So we'll say sum of square residual is equal to 23.49. And that's it for how to calculate sum of square residual. So the sum of square residual is not that bad to calculate. The only thing is, it does take a lot of steps, because first you have to calculate the least square regression model. Once you calculate the least square regression model, then you have to find the predicted value. Then you have to go ahead and find the residual. And then you finally go ahead and do the residual square. So if you look at it, it's not that bad to calculate. It takes a lot of steps to calculate. But like I said, in the test or in the quiz, I'm not going to expect you to know. Well, I'm not going to expect you to calculate it, but you should know what does the sum of square residual represent. Any question for the sum of square residual? All right. So if you look at our sum of square residual is 23.49, which it is pretty close to zero, but it's kind of hard to distinguish without comparing it to something else. Because you kind of want to see how good of a model you have. So usually when you calculate the sum of square residual, it's when you have two different models and you want to see which of the two model is doing a better job of making the prediction. So let's say we have model A, and let's say model A, we're doing a least square regression line. And say model B, this one we're doing a parabola. In case you forgot what a parabola is, a parabola is either going upward or going downward. So say when we do the sum of square residual for a model A, which is the least square regression line, say we get sum of square residual, and let's say we get 10. Say we do model B, and model B, we do the sum of square residual for it, for the parabola, and say we get sum of square residual of 5.7. So which of the two did a better job on modeling our data set? Model A or model B? All right, so we got 1 for model B, 2 for model B, any more for model B? Yeah, so if you look at this one, since model B have a smaller, what do you call it, have a smaller sum of square residual, model B will be the best model for this data set. So we'll say, since model B, all right, so we'll say since model B has the smaller SSR of the two models, that tell us that the parabola fit the data better than a least square regression line. Because you usually don't ever want to just go with one model. You usually want to try and check out a couple of different models just to see if a different model will yield you a better SSR. But usually, if you just look at the scatter plot, you can kind of tell what type of model will be best for your data set. But that's it for a SSR. Any question in regard to SSR or sum of square residual? No. Alrighty then. Let's move on. All right. So the last thing we're going to learn in 4.3 is something called influential observation, or influential observation, or influential point. Influential points are either points that kind of stand out, that are far away from the regular data set. Kind of think about it as an outlier. So it's a data set that doesn't quite fit in, and that one data set influences your R value significantly. So usually the way that we could tell if we have an influential point is whether if we include the data point and whether we take away the data point, if your correlation coefficient or R or your slope or your Y intercept, is that drastically changed once we pretty much exclude that point? If that significantly changed one of those three or all of those three, then you could say that you have an influential point. So you to kind of visually see an influential point, here is that. So if you kind of look at it, you have all of these blue data sets, which all of these blue data sets are kind of stuck together. that table. Back up. So if you look at these two, well, sorry, if you look at these 5 points, those 5 points pretty much gel together. But if you kind of look at it, it doesn't look anything like a line. If I'm just looking strictly at the 5 blue dots. But once I introduce the 6th dot, which is the red dot, that red dot, like you can kind of clearly see that that dot doesn't belong with the other dot. So it might be considered an influential point because that dot is such a further away from all the other dots. Because what this influential point will cause or will make happen, it's gonna make where our R value is either increase or decrease, because what's gonna happen, the R value is just gonna look at the 6 and you think that it's the other dot. So if you connect all of the blue dots with the red dot, now you're gonna think you have a strong linear correlation, which isn't true because you only have one random dot there. Cool. So that's one example of an influential point, when you have a bunch of points at one area, and then you have this one random data set far beyond the other data set. That's an influential point. All right, here go other influential points. So if you look at the blue dots again, the blue dots pretty much are data set. If you look at it, they look like a linear model. And if you look at it, I calculate the linear line. So this is the linear line with only the blue dots. So if you look at the blue line, that's the linear model only if I include the blue dot. So in this one, I'm not including the red dot. But look what happened to the linear model once I include the red dot. So based off of just looking at the red dot, or sorry, the red line and the blue line, did the red line drastically change once we introduce once we introduce the influential point? Cool, yeah. So like what's happening, this blue line, it want to get closer to that red line. So in order to get closer to that red line, if you kind of look at it, to that red dot, this line over here is getting drastically closer to it. So that's why you always have to be careful with the influential point, because influential point will drastically change your model and will drastically change your R value. All right, so let's do an example of it. So here is my data set. So my data set is X is 1 and 5. My second point is 2 comma 4. My third point is 3 comma 5. My fourth point is 2 comma 3. And my last point is 20 comma 21. So if you have your notes, do a scatter plot for that data set. So the first one is 1 comma 5. So 1 comma 5 is here. Next one is 2 comma 4. 2 comma 4 is here. If you look at 3 comma 5, there, and then 2 comma 3. And then you have 2021. All right, so those are my 5 scatter plot. Any question on so far on just the scatter plot? All right, so let's label this. So let's label A, this is B, this is C, this is D. Let's say this is E. So of these 5 points, which point do you think is a which kind of influential point? Perfect. So we're going to say that E is an influential point. So what I want to do, what we're going to do, we're going to calculate the R value and we're going to calculate the slope and the y-intercept on our calculator to see what's our y-intercept, slope, and R value with the influential point, and then we want to see it without the influential point. So we're going to calculate R, we're going to calculate the slope, we're going to calculate the y-intercept. So we're going to do with, and we're going to do it without the influential point. So take a minute right now, and I want you to calculate what the R, what the slope, and what the y-intercept will be with the influential point. And then what we want to do, we're going to do it without the influential point. So I'm going to go ahead and do transition over to my TI 84. There we go, stats. Let's go to edit. So first thing I want to do, I want to clear up my list. So I'm going to press clear, enter. And then for L1, we'll press clear, enter. So we'll say 1, 2, 3, 2, and 20. And then we'll do Y, which is 5, 4, 5, 3, and 21. So now I'm going to go ahead and go to stats, go to calculate, and we're going to do linreg ax plus b. All of that should stay the same because I didn't change anything. All right, so if you look at my R value, R is 0.99. If you look at what we get for our slope is 0.92. And lastly, for our y-intercept, we get 2.43. All right. Any questions so far how I got the slope, the y-intercept, and my R value? Okay, so what I'm going to go ahead and do, I'm going to go back to stats, and now I'm going to do without the influential point, or without the point that we think is the influential point. So now what I'm going to go ahead and do, I'm going to go ahead and delete 21, and I'm going to delete 20. And now I want to see, does my R, my slope, and my y-intercept, does that drastically change? Because if it drastically changed, that's telling me that 20 and 21 was an influential point. If it doesn't drastically change, that's telling me it's not an influential point. So let's go to stats. Let's go over to calculate. Let's go to linreg ax plus b. All right, so let's do R, slope, and beta naught. So if you look at R is actually equal to 0. Our slope is actually equal to 0. And my y-intercept is equal to 4.25. So what do you think? Do you think that the last point of 2021, do you think that point is an influential point? Or do you think it's not an influential point? Yeah, so we'll say, and let me actually share my screen. So say yes, 20 comma 21 is the influential point since R slope and the y-intercept change drastically. And that's it for influential point. Any question in regard to influential point? All right, so let's go down. Okay, so up next we're gonna get into something called a contingency table. So for a contingency table, they usually call it also a two-way table. So when we have a two-way table or a contingency table, what that is, it means that we have a table and we have two categories. So we usually have where category A, and then we have category B. So you're always going to have a category for your column and you're going to have a category for your rows. So just know these are your columns. So whenever I'm talking about columns are these. Whenever I'm talking about the rows, I'm talking about these. So you kind of know the difference between the rows and the columns. Yeah. So what we're going to learn in this section, we're going to learn something called marginal distribution and conditional distribution. So for marginal distribution, whenever we want to find a marginal distribution, we're finding the probability of either that column occurring or that entire row occurring. So whenever we say marginal distribution, we're either going to find what the probability of that particular column occurring or what is the probability of that entire row occurring. So that's what a marginal distribution is. Any question for marginal distribution? Okay, up next we're gonna go into conditional distribution. A conditional distribution, well, kind of think about the word conditional. Conditional means we have a condition. So whenever we have a condition, that means we're not gonna use the entire row or the entire column. We're essentially just gonna use a particular part of that two-way table. So we're not gonna use all of the data set. We're only gonna use a particular amount of that data set. All right. So for a conditional distribution, you're only using a subset of the data set. For a marginal distribution, you should always divide by the total. So for this one, divide by the total. For this one, you do a subset. Any questions so far on conditional versus marginal distribution? All right, so let's go ahead and do this problem. All right. So for this two-way table, pretty much I have Derek Jeter. So what I have in regard to Derek Jeter is pretty much whether Derek Jeter got a hit or he doesn't get a hit. And then I have LHP, which means the left-handed pitcher. So that means the pitcher throwing to him is left-handed, or RHP, which means right-handed pitcher. So LHP just stand for left-handed pitcher, and RHP stand for a right-handed pitcher. Right. So let's do part A. So if you look at part A, it says, how can we find the total for the row and for the column? So if I want to find the total for Derek Jeter get a hit, how can I find the total of that? Well, what should I add? Should I add all the numbers? Should I have some of the number? And which number should I add up? Yeah, so you want to add up 8,332 and you want to add it to 2863. So let's add those two number up. So 2863, oops, no. So 2863 plus 8332. Perfect. And you get one, well, not 1,000, 11,195. So, all right, so let's go ahead and get this total now. They do 952 plus 2513. So you get 300, well, sorry, 3,465. So now let's go ahead and get this row right here. So to get this row, you have to do the 952 plus the 2,863. So 2,863 plus the 952, and you get 3815. Lastly, we're going to do 8,332 added to 2513, and you get 10,845. And then the last one going to be the total amount. So in order to get the total amount, I can either add these two numbers right here, or if you want, you could add these two numbers right here. And like a good practice, you want to add both of those numbers because both of those numbers should give you the same value. So if I do 11,195 added to 3,465, you get 14,660. But you can also check that if you do 3,815 plus 10,845, you should also get 14,660. So let me double check that. Yeah. All right. So we're all done with part A. Any question in regard to part A? All right, let's do part B. So for part B, it said what percent of the time does Derek Jeter get a hit? So for this one, we're gonna say probability, and we just want to find the probability he get a hit. So usually when you see this P right here, that is mean for probability or percent. It's the same thing. So anytime I do that notation, and if I do that notation on a quiz or on a test, you should know that that just stands for find the probability. So for this one, does it matter if Derek Jeter is hitting versus a left-hander pitcher or a right-hander pitcher? Or do we just care about him just getting a hit? So like we just care about him getting a hit. So how many times did Derek Jeter get a hit? 11,000. Oops. 195. Oh, I think I did this number wrong. Okay. How many times did Derek Jeter bat? 4,660. Cool. All right, so let's divide this. Yeah, this is totally wrong. All right, so what percentage do we get? 0.7636. All right, FYI, this probably completely wrong. He did not get a hit 76% of the time. I need to change the numbers. Change numbers. All right. So let's do C. So for this one, said what percent of the time the Derek Jeter was batting versus a left-handed pitcher? So for this one, it says what percent of the time the Derek Jeter bat versus a left-handed pitcher? So for this one, if you want to find out how many times did he bat versus a left-handed pitcher, once again, for this one, we're not looking at anything more. We just want to find out how many times did he hit versus a left-handed pitcher. So how many total times did he hit versus a left-handed pitcher? Yeah, so 3,815. And you want to just divide that by the total, which was 14,660. So you go 3,815 divided by 14,660. So you get 0.2602. And just know that this is decimal form. If I want it in percent form will be 26.02%. So just know the difference between percent form and decimal form. All right, but that's it for C. Any question in regard to C? Why is not the total? Well, because if you look at this one, we don't want the total hits. Because if you look at it, it says what percent of time did Derek Jeter bat versus a left-handed pitcher. So we just want to see, like, of all of the time he was on play, how many times was he batting versus a left-handed pitcher. So it doesn't matter if he got a hit or didn't get a hit. All we care about is how many times was he batting versus a left-handed pitcher. All right. So let's go on to this next one. And also, in case you were wondering, both of these are marginal distribution. Because if you look at it, we both time we divide it by the total amount. All right then. All right, so I'm going to go ahead and do this two-way table. So for this two-way table, it has two categories. So the first category is which hospital they went to. So that's this. What hospital did they go to? And pretty much then you have patient status. So whether they survived the hospital stay or they didn't survive the hospital stay. So if you look at part A, it's in compute the marginal distribution of both variable. So for this one, you want to find all of the marginal distribution for both variables. So what's one of the marginal distribution I could find? So if I wanted to find the marginal distribution of this, what would I call that? I will find the probability of what? Well, that's the patient status. Okay, if you look at which row did I highlight? I highlighted the row hospital A. There we go. So this will be the probability somebody went to hospital A. All right, what's the other probability that I could find? That's a marginal distribution. All right, hospital B, perfect. What's the other marginal distribution I could find? Perfect, so they survive. Lastly, what's the last marginal distribution I could find? Theta. Perfect. right. So for this one, we want to go ahead and do, we want to find the probability that somebody went to hospital A, somebody went to hospital B, somebody survived, and somebody died. So let's go ahead and do this. So how many total people went to hospital A? 2,100. How many total people went to the hospital? Cool. 2,900. So let's do 2,100 divided by 2,900. You get 0.7241. So we roughly get 72%. So 72% of people went to hospital A. All right, let's find hospital B. How many total people went to hospital B? 800, good. Same thing out of 2,900. So if I do 800 divided by 2,900, what should I get? Cool. All right, so you should get 0.2759. All right, so if you look at it, hospital A and hospital B, since those are all of the category for that variable, if you were to add the two probability up, or if you were to add the two fraction up, it should always add up to 1. Because if I have all of the marginal distribution for the column or for the row, all of those probability for the column or all of the probability for the row should add up to 1. All right, any questions so far in regard to probability hospital A or probability hospital B? All right, so let's do probability somebody survived. So the probability somebody survived, how many total people survived the hospital? Yeah, so 28, 21, and you divide this by 2,900. So if you do this, you get 0.9728. Everybody go on probability somebody surviving. All right, what's the probability somebody die? So 79 out of 2,900. And somebody already got that for me, 0.0272. Thank you, Javier. All right, and that's it for A. So these are all marginal distribution, because if you look at it, we didn't put any essentially caveat or we didn't put a condition in it. We just want to find out how many people, the percentage of people who went to hospital A, percentage of people who went to hospital B, percentage of people who survived, percentage of people who died. All right. Everybody go for part A. All right, let's do part B. All right, so up next, we're gonna go ahead and we're gonna do part B. So for part B, it says use the conditional distribution to identify association among hospital and survival status. So right now, what I wanna do, I wanna see if there's association between the hospital that you go to and whether you'll survive or not survive. So for this one, what I'm gonna do, I'm gonna say the condition is the hospital. So for this one, we're gonna say the condition is gonna be the hospital that you go to. So I want to see, does it make a difference which hospital do I go to? Like if I go to hospital A, do I have a higher chance of surviving than if I go to hospital B? Do I have a lower chance of surviving in hospital B? So what we're gonna do this based off of which hospital you go to. So this one gonna be hospital A. This one gonna be hospital B. So what we want to do, we want to focus on the percentage who survive. So right now what we're gonna do, we're gonna make the condition. The condition we want it to be that the condition is which hospital do they go to. So instead of looking at all of the data set, what we're gonna do, we're gonna just focus on that condition. So let's go ahead. Right now, we're gonna get focused on people who went to hospital A. So if I'm just focusing on people who went to hospital A, how many total people went to hospital A? 2,100, perfect. So for this one, and you know what? Let me put a little bit more space right here. So right here, we're gonna divide by 2,100. Because the thing is, since we're putting the condition that they had to have gone to hospital A, I don't want to focus on people who went to hospital B. I just purely want to focus on people who went to hospital A. So let's go back and focus on people who went to hospital A. So of the people who went to hospital A, how many of them survived? Cool. So we'll put 20, 37 here. So if you went to hospital A, the probability that you survive will be 2,037 divided by 2,100. So let's take a minute and let's calculate that in our calculator. Cool. All right. So what do we get for that one? All right. So we got 0.97. All right. So let's go ahead and now let's do that for people who went to hospital A. How many of them died? So if I go over here, how many total people that went to hospital A died? 63, perfect. So right here, we'll put 63 out of 2,100. So we'll say 63 divided by 2,100. And what do we get? Good. Sorry about that. So you get 0.03. And if you look at it once again, if I add those two up, it add up to 100% because essentially those are all of the category that could happen for people who went to hospital A. You could either survive or you could die. So there's 100% chance that one of those two will happen. So that's why when you add up those two probability, it add up to one. All right, so now let's do this for hospital B. So for how many total people went to hospital B? 800. Of these 800 people, how many of them survived? 784. So if I do 784 divided by 800, I get 0.98. Cool. All right. So for this one, you get 800. So of the 800 people who went to hospital B, how many of them survived? Oh, sorry, how many of them died? 16. So if I do 16 divided by 800, you should get 0.02. Perfect. All right, so if you look at it, if I do probability they survive given they went to hospital B and probability they die given they went to hospital B, they add up to 100%. If you do 0.98 plus 0.02, you're going to get 1, which of course is 100%. Any question in regard to that conditional probability? All right. So like the one thing I do kind of want you to notice is kind of notice like we're not using the entire table. You're only using the pretty much the condition that we're kind of focusing on. So for this one, does it make a difference which of the two hospitals do you choose, or like are you more likely to survive in one than the other? Yeah. So if you look at it, it doesn't really matter which of the two you choose to go to, like the chances of you surviving or not surviving. are pretty much the same because at hospital A, you have a 97% chance of surviving versus in hospital B, you have a 98% chance of surviving. All right, sweet. So that's it for B. All right, so let's do C. So for C, it said draw a bar graph that represents the conditional distribution of survival status by hospital. Comment on any type of association that may exist between the two. All right, so if you look at this one, we want to do a conditional distribution bar graph based off of the hospital they went to. So right here, we're going to say hospital A. Right here, we're going to say hospital B. All right, so we're going to do two graphs. So we'll color coordinate this. So we'll say if it's red, we'll say they survive. If it's green, we'll say that they die. So let's go ahead and do hospital A. So hospital A had a 97% survival rate. So we'll say all right, so that's the survival rate. And then we're going to do the percentage of people who die, which we'll do in green. So green with 3%. So not over. All right, and that's it. So that's the bar graph for a conditional distribution for hospital A. So now we're gonna go ahead and we're gonna do this for hospital B. All right, so for hospital B, it was 98%, so slightly. All right, so that's pretty much the bar graph for people who survive, and then we'll do one for people who die. All right, that didn't work. And we'll stop trying. All right, and that's your bar graph for people who die given they went to hospital B. So if you look at both bar graphs, they're relatively the same height. So that's kind of telling us there's not that much difference. So that's kind of telling us there's no association. Because whenever we're talking about association, we're trying to see, does it make a difference if I go to hospital A or hospital B? But if they're relatively the same, pretty much that's telling us there is no association. So whenever we're looking for association, we're trying to see if there's a drastic difference between going to hospital A or going to hospital B. So in this case, since there is no drastic change between survival rate, if I go to hospital A or if I go to hospital B, that's why we say there's no association. So this one will say no association. And we're done with that one. Any question in regard to the last problem? All right, let's scroll on down. All right, so this next one, same concept. So if there was an association, you'll say there is an association between the patient status and the hospital they went to. So you either say that, or you could also say like what the association. So you could go like, if you go to hospital A, you're more likely to survive, versus if you go to hospital B, you're less likely to survive. So you can either say yes, there is an association between the hospital you go to versus what you call it versus the patient status, or what you could do, you could just say, if you go to hospital A, you're more likely to go or more likely to survive, versus if you go to hospital B, you're less likely to survive. Any other question in regard to the last problem we just did? There a question or no question? Yeah, so it depends on the condition probability that you get. So if the condition probability that you get, if there's a drastic difference between the two, we say there is an association. But if there is no difference between the two percentage, then we say there is no association. So let's go ahead and do this next problem. So for this next problem, we're focusing on babies, and we're trying to focus to see if ultrasound predictions, if they're accurate. So we want to see how accurate is the ultrasound prediction. So we're trying to see, is there association between the ultrasound prediction and the gender? So we want to see, is it more accurate for female or is it more accurate for male? So if your baby is a male, is it more likely to predict it that it's going to be a male? Or if a baby is female, is it more likely to predict it that it's going to be female? So the way that we should read the two-way table, if you look right here, it's a ultrasound predicted female. So what that mean? It means they went to the hospital, they got a doctor, the doctor did an ultrasound, and based off of that ultrasound, the doctor predicted the baby should be female. If you look at this one, once again, they went to the doctor did the ultrasound on the belly, and the doctor predicted the baby should be male. So that's what the top two columns are telling us. What this is telling us once the person had their baby and they recorded the gender of the baby. So they said the baby was female or that the actual baby was male. All right. Everybody good on what the table is telling us? Super. All right, so let's do part A. So for part A, it says find the probability a newborn baby is female. So if you look at part A, it is asking us, hey, what's the probability that this baby is female? So for this one, should I divide by the total or is this a conditional probability? Well, for this one, what's the condition? If there is a condition. But do they tell us the baby was our like? Do they? Because whenever they tell the conditional is telling us this is information we already know. Like, do they already tell us we know the baby was female? Like, if you look at the problem, they just want to know what is the likelihood that the baby is female. So for this one, it's actually not a conditional distribution. This is a marginal distribution. So this is a marginal distribution. So if I say prediction. Well, if you look at it nowhere in the problem for part A, it doesn't say anything about a prediction. It is saying what is the probability that the baby is female. So it's saying telling us we don't know the likelihood of this occurring, so it's telling us to find it. So this one should be marginal distribution. So we're gonna find the probability this baby come out to be female. So how many baby actually turned out to be female? So there's only 432 babies that were actually female? There should be more than that. There you go. It actually should be 480. Because this is saying there's 432 female that were predicted to be female. And this is saying there's 48 female that were predicted to be male. But these both are female. So for this one, it will be 480 divided by 1,000. So if I do 480 divided by 1,000, this one should be pretty simple. You should get 0.48. And that's it for that first part. Any question in regard to that first part? All right, let's do B. So if you look at B, it says find the probability a newborn baby is male. All right, so we just want to find the probability that a newborn baby is male. So for this one, there's no conditional distribution. We just want to find what is the likelihood that this baby actually turned out to be a male baby. So this is a marginal distribution. So how many baby actually turned out to be a male baby? Yeah, 520, perfect. And then you have 1,000. So 520 divided by 1,000 will give you 0.52. And that's decimal form. All right, and that's it for B. So A and B, both of those are marginal distribution. I'm gonna give you a little heads up. C and D are gonna be conditional distribution. So let's do C. Any question in regard to B before I move on to C? All right. So let's do C. So for C, it said use the given information to estimate the probability that a newborn baby is female, given that the ultrasound predicted the baby will be female. So for this one, do I already know the baby is female, or do we already know that the ultrasound predicted the baby will be female? And I'll tell you, well, which one do we know? We either know the baby is female, or we either know the baby was predicted to be female. Cool, perfect. Ultrasound predicted. So the kind of easy way to kind of know what the given or what the condition is the keyword given that. So given that, and then whatever follow, that's your condition. So in this case, the condition is the ultrasound predicted the baby will be female. So I'm gonna put right here, condition is ultrasound predicted the baby would be female. So that's the condition. The condition is that the baby was already predicted to be female. So that means they went to the hospital, the doctor did the ultrasound, and the doctor told them that your baby is going to be female. So what we want to do, we want to find the probability of that. So let's go ahead and find the probability of that. So first we want to put the condition that the ultrasound predicted the baby will be female. So how many total baby were predicted to be female? All right, so the battle between 432 and 562. So the winner of that battle will be 562. Because remember, we're looking for how many total baby were predicted to be female. So for this one, we don't care if they actually turn out to be male or actually turn out to be female. We just care about how many baby were predicted to be female based off of the ultrasound. So the 562, that's what we divided by. So of these 562 baby that were predicted to be female, how many of them actually turned out to be female? Cool. So it should be 432. Because remember, we're only looking at baby that were predicted to be female. So you're only focusing on this column. So I'm not focusing on the entire picture. I'm only focusing on ultrasound predictive female. So once you know the condition and the condition is ultrasound predictive female, you're only looking at that column. So I'm not looking at this because that's including this 48. But like I said, we're only going to focus on ultrasound predictive female. So that's one thing about the conditional distribution. Like once we get the condition, you only want to focus on that condition or how many people pretty much does that condition apply. So for this one, we're going to do 432 divided by 562. 432. Yeah. Any question why we got 432 divided by 562? All right, so let's go ahead and do that math. So you do 432 divided by 562. And you get 0.7687. So roughly, if you look at it, 76% of the time, if a baby were predicted to be female, 76% of the time they actually turn out to be female. So that's kind of telling you like 3/4 the baby that were predicted to be female actually end up being female. The other quarter of the baby, they actually ended up being male. So that means the ultrasound got it wrong. So telling you 76% of the time the ultrasound is actually going to predict it correctly. The other 24% or other 23% is actually going to be incorrect. But that's it for part C. Any question in regard to part C? All right, let's do part D. So part D says use the given information to estimate the probability that a newborn baby is male, given that the ultrasound predicted the baby will be male. So for this one, what is my condition? Like, what is the condition that they already tell us we know? Like, do I already know the baby is male, or do I already know the ultrasound predicted the baby to be male? Yeah, so the condition is ultrasound. Oops. Hold me there. All right, so that's the condition. The condition is ultrasound predicted the baby will be male. So since that's the condition, that means we're only going to focus on baby who the ultrasound predicted to be male. So here, let's do some blue. All right. So let's go ahead and find this. So how many total baby were predicted by the ultrasound to be male? 438. So yeah, so it's 438. Because that's how many total baby were predicted to be male. Of the 438, how many of them actually turned out to be male? There you go, 390. So let's go ahead and do 390 divided by 438. If you divide that, what do you get? There you go, 0.8904. All right. So if you look at it, they're kind of telling you like the accuracy of the ultrasound given, they already told you. So kind of imagine like if you go to the doctor, if the doctor tell you based off of the ultrasound, your baby gonna be a female, there's a 24% chance that the baby might actually turn out to be male. But if the ultrasound predicted that the baby will be male, it's telling you there's an 89% chance that that will be correct. So they're telling you there's a 10% chance that the baby, if the ultrasound predicted male, will actually be female. So for this one, we're gonna go to part E. So it says, based on your answer to part C and D, do you think the ultrasound is equally reliable for predicting gender for boys and for girls? Explain. So do you think they both do a good job at predicting the gender of the baby, or does it predict the gender of the baby a little bit better for one gender versus the other gender? Yeah, so let's say the ultrasound So we'll say the ultrasound is better at predicting boy versus girl. So for this one, we'll say there is an association. So we'll say there is a, uh, right. So we'll say the ultrasound is better at predicting boy versus girl because if you look at it for boy, 90% of the time it get it correct. For girl, it only get it correct roughly like 77% of the time. So it's a little bit more reliable for male versus female. So in this case, we'll say there is an association between gender and the ultrasound reliability. If both of the percentages were the same or roughly the same, then we can say there is no association because it doesn't matter if the ultrasound predicted female or male, it does an equal job of predicting it. But for this one, since there's like a 13% difference, we're gonna say there is an association. And that's it for this last problem. Any question for that last problem? All right, cool. All right, and that's it for this chapter 4. So here goes some links. So if you want to know how to do a scatter plot, find R linear regression on the calculator, that's where you want to go. So if you're still having trouble finding R using the calculator, finding the linear regression using your calculator, or doing a scatter plot using your calculator, just click on this link and that should help you out. If you need help on finding R by hand, just click on that link and it'll help you find R by hand. All right. But that's it for chapter 4. Any question in regard to chapter 4? Wait. All right, so that's going to be it for today's lecture. So for tomorrow, there's not going to be a quiz since you just took an exam. So I really don't want to give you a quiz right after your exam. So for Tuesday, there's not going to be a quiz. So that means on Thursday, there will definitely be a quiz, and the quiz will cover whatever we go over on Wednesday. Any questions? Cool. All right. So there's no question. That's pretty much it for today's lecture. I'll see everybody on Tuesday. So just remember, if you still haven't turned in the homework, turn in the homework as a singular PDF file. And by the end of Wednesday, I should have all of the tests graded because there are, I think, like 7 or 9 questions I need a grade. So I'll have that graded for sure by Wednesday. All right, so that's it. Have a good night. I'll see everybody mañana.